All right, let's go ahead and get started with section 3.2. In this section, we're going to be looking at the variation in the repeated outcomes where we have an unequal proportion across the categories. In the previous section, we looked at the variation in the repeated outcomes, but each of the categories had the same parameter setting. And here, we're going to allow that to differ. Okay, let's go ahead and get started then. So in this singing case study that was presented in section 3.1, the four parameter values of interest had the same value. So we were looking at the chance or the probability that the winner would be selected from the first set. That was set at 25%. And that was the same across the second set, the third set, and the fourth set. Now the calculations that we used in method 1 when we considered the absolute distances, or in method 2 where we were squaring those distances, will need to be modified when the parameter values are not all the same across the categories. And that's the purpose of section 3.2. So let us consider example 3.2.1. This example is centered around the Minnesota Student Survey, which is a survey that is administered to 5th grade, 8th grade, and 11th grade students throughout the state of Minnesota. This survey is an important vehicle for the youth voice in Minnesota, and many different people use this survey to inform their community initiatives and prevention programming. The questions on this survey are quite extensive and deal with home and school life of students. They include family relationships, feelings about school, substance abuse, wellness activities, etc. The participation in this survey is voluntary, confidential, and anonymous. And there's the website there if you'd like to go check out outcomes from this survey. I use that website there to gather the data that I'm using for this example. So we are going to deal with the following question, How much do you think people risk harming themselves physically or in other ways if they smoke 1 or more packs of cigarettes per day, have 5 or more drinks of alcoholic beverage once or twice a week, smoke marijuana once or twice a week, or use prescription drugs not prescribed to them? And I'm going to be considering outcomes from Fillmore County. Fillmore County is actually where I live. We have 4 children, and that's where they go to school, is in Fillmore County. So recent outcomes from the Minnesota Student Survey, as I said, can be downloaded from the website provided here. I went ahead and gathered information for Fillmore County. Now there's a lot of data here, and we're going to focus on just one set of these numbers. So what set are we going to focus on? I'm going to focus on the grade 11 students, okay, over here on the right-hand side. And then the question that dealt with risk harming themselves with 5 or more drinks of alcoholic beverage 1 or twice times per week. Now this table has the data broken out by females and males, but I'm not going to be concerned about differences between genders. So what I'm going to do for our analysis here is just add the 8 and the 12 to get 20. So 20 people here thought that drinking 5 or more drinks would be of no risk. So there's 20 people here for that no risk row. There's 31 people here for the slight risk row, 16 plus 15. For moderate risk, I had 21 and 14, so that was 35. And then for great risk, I had 19 and 20 for a total of 39. So the data that I'm going to be analyzing here are those totals across both genders for grade 11. Again, those were 20, 31, 35, and 39. So I went ahead and just put those numbers into a spreadsheet and created the following simple graph here. This is just a segmented bar graph where the outcomes from each category are listed. So I had 20 people under the no risk group, 31 people in the slight risk group, 35 in the moderate risk group, and 39 in the great risk group. So we can see that the proportions here are not close to being the same. There's quite a bit more people that think drinking more than 5 drinks once or twice a week is of great risk here. That proportion is pretty high at 39%. Now this information that is presented here is for the students in Fillmore County. So I selected Fillmore County when I was downloading this information. So what we're going to do is compare the outcomes from Fillmore County against the historical percentages for the state of Minnesota. So the research question is stated here: is there evidence to suggest grade 11 students from Fillmore County deviate from the historical patterns of other students throughout the state of Minnesota? In order to do this test, I'm going to need to know what the historical patterns are for the other students throughout the state of Minnesota. And that's what this table presents here. That's on the middle of page 17. In the no-risk group, from the historical patterns, about 8 out of every 100 students fall into that category. So about 8% fall into the no-risk group. So 8% of the students in Minnesota believe drinking 5 or more drinks is of no risk to them. For slight risk, that percentage goes up quite a bit. That percentage goes up to 22 out of every 100 students. For moderate risk, that percentage is 30 out of every 100 students. So that would be 30%. And then the great risk category has the largest percentage, which is 40%. So I'm going to have, again, 4 different parameter values for this particular example. I'm going to have the probability that a student will identify with no risk. And again, the historical patterns for the state of Minnesota, that is going to be set to 8%. For the slight risk, that will be set to 22%. For the parameter for moderate risk here, that one is going to be set to 30%. And then the parameter for great risk will be set to 40%. So we can go ahead and construct a composite hypothesis with those percentages again. That's what we've done here on the top of page 18. We are once again, like we did in the previous section, simply going to compare the observed counts to the expected number for each category. So now that I know what the percentages are for the historical patterns, the 8%, 22%, 30%, and 40%, I can use those to compute my expected number. So what do I do for the expected number? Well, I take the total number of students that are being considered here, which there were 125. So I had information on 125 students from Fillmore County. Recall that the observed counts here were 20, 31, 35, and 39. But there was 125 in total from Fillmore County. I'm going to take that 125 and multiply that by the 8% in order to determine the expected number for the no-risk group. The expected number for the no-risk group is 10. I'm going to do that for each of the other categories. So for example, in the great category, the great risk category, 125 students, about 40% of them should be saying that drinking more than 5 drinks once or twice per week is of great risk. So I should have about 50 students from Fillmore County saying that. I only had 39, so I'm a little bit under the expected number there. Also, I guess, I'm a little bit over the expected number on the no-risk category. So it may appear that students in Fillmore County are a little bit more laxed about the substance abuse of alcohol compared to other students across the state of Minnesota. Now, the statistical investigation is going to need to take into consideration the fact that over repeated sampling, the outcomes are going to vary from year to year. So these outcomes are 20, 31, 35, and 39. Certainly, if I collect data next year, these numbers are going to be different. Okay? But my statement here, the research question, is asking not about just students from this particular year, but it's asking about grade 11 students from Fillmore County. So the scope of inference here is grade 11 students from Fillmore County. Now I just happened to gather information on 125 students in order to conduct this analysis. So we're using the information from this particular year to try to generalize what we can say about opinions in Fillmore County for grade 11 students. So we have the observed data, again the 20, 31, 35, 39, but there's going to be some margin of error or some variation from year to year, as I just stated, in these numbers. Okay, so I want to determine whether or not these numbers here, the pattern 20, 31, 35, 39, deviate enough away from the pattern of 10, 27.5, 37.5, and 50. So that's the goal of the test here, is to determine whether or not the observed counts are close enough to the expected counts when I take into consideration this notion of the repeated variation from sample to sample. So what is the simulation model? Well, the simulation model is simply going to be very similar to what we've done before. We're going to create a hat where the probability of each outcome is specified from the parameter values that we set up above. So the no risk group, again, was 8% from the historical patterns. Slight risk was 22, moderate risk was 30, and great risk was 40. So I'm going to set up my hat assuming the students from Fillmore County follow the trends from the rest of the state. I'm going to select 125 people out of this hat because that's the number of students that we obtained from Fillmore County for our study. So again, I reach in here, I'm going to pull out 125 pieces of paper, and I'm just going to tally up how often I got a no risk, how often I got a slight risk, moderate risk, and great risk. So for this first simulation outcome, it looks like that pattern was 13, 24, 32, and 56. Again, if I add that up, there's going to be a total of 125 there. That's going to be the same for each simulation run because that's how many people I'm pulling out of the hat here. Now, some of these are going to be closer to the expected than others here. So if we recall, the expected counts here were 10, 27.5, 37.5, and 50. So some of these simulated outcomes are going to be pretty close to that. For example, this one right here is pretty close. 9, that's pretty close to 10. 27, yep, that's really close to 27.5. For moderate risk, I should see about 37 or 38, pretty close to 40 there. Okay, and great risk, I should see 50, and I obtained 49 on this particular simulation run. So I would anticipate that these here are going to be pretty close to the expected outcomes. And we're going to use our observed data. Okay, so we're going to take our observed data and compare that to those expected outcomes under a situation in which Fillmore County kids follow the rest of the state of Minnesota trends. So we're going to take, just like we did before, we're going to take each one of these numbers and build a pyramid. Okay, so we have that on the left-hand side here. Just building the pyramid for no risk, slight risk, moderate risk, and great risk. And I'm just going to use these values that we obtained up above in order to build those pyramids. So there's really nothing new here from what we considered in section 3.1 up to this point. We're going to then apply the 5% rule, the two-sided 5% rule, to each one of those pyramids. And we're going to determine whether or not our observed outcomes fell within or out of the likely range. So for the no-risk group, we can see that the upper cutoff is about 18 or so. 20 does not fall, or excuse me, 20 falls beyond that upper cutoff. So 20 is going to indeed be an outlier. So let's go ahead and mark that as such. How about the slight risk group? For the slight risk group, the outcomes from Fillmore County, which were at 31, fall within the realm of what it would look like if it followed the state trends for slight risk. Okay, so For the slight risk category, I'm not an outlier. So let's go ahead and mark that as such. How about the moderate risk group? For the moderate risk group, I obtained 35. I should have seen about 37 students in this moderate risk level. So I'm real close to what I expect there. So that's definitely not an outlier. How about the great risk group? The great risk group is starting to get on the edge. Okay, so that may be an outlier. All right, but it is within the cutoff values here. It looks like the cutoff values might be about 36 or 37 or so. So 39 does not quite meet that threshold. So I can go ahead and identify that as a no. If you want, you maybe could put a maybe in here, like we did before for the earlier example, but it doesn't quite meet that threshold. Okay. Now let's go ahead and compute the distances across those four categories like we did before. All right, so what we're going to do is just simply take the 20, which was the observed outcome for no risk, subtract the 10. So 20 minus 10, I get a positive 10. Okay, I'm going to square that. I'm going to go ahead and square that quantity using method 2 here, the squared distances. So 10 squared is actually 100, so that math is pretty easy there. Okay, for the second group, for the slight risk group, I observed 31. I should have seen 27.5, so about 27 or 28. I take 31 minus 27.5, I end up with positive 3.5. And I square that quantity. So that quantity squared, I guess. Let's go ahead and grab my calculator here. 3.5 squared is indeed the 12.25 as is shown here. I'm going to continue that for the moderate risk group. Again, 35 is pretty close to the 37.5, so that squared quantity there is going to be pretty small. And then over here for the great risk group, the observed quantity was 39. My expected was 50. 39 subtract 50 is negative 11, and negative 11 squared is 121. Now, just looking at these squared distances, it looks like this one is pretty darn small. That's pretty close. So we're not very far from the expected there. Certainly, if we look at the numbers, we can see that 35 is indeed pretty close to the expected number. Likewise, for the slight risk group, we're pretty close to the expected number here. We do have a pretty substantial distance here for the no risk group. We're at about 100. But the biggest distance here is occurring at the great risk group with a squared distance of 121. So that would let us believe anyway. So it appears that the outcome for the great risk category is the furthest away from the expected. Okay, so it appears to be the biggest outlier here because that squared distance is bigger than any of the others. But there's a fault in that thought process. So let's go ahead and just look at the graphs real quickly. So as I just said, it appears that the great risk category has the largest distance and thus would be the most extreme across the four categories. But from our graphs, we can see that the no risk category here, so the no risk category here, actually appears to be more of an outlier than the great risk category. So being 10 away, 20 minus 10 here, the observed outcome for the no risk group was 20. The expected is 10. So I'm 10 away from what I expect. That appears to be more of an outlier than this one down here that is 11 away from what I expect. And the reason that is happening is because the amount of inherent variation that exists in the great risk pyramid is bigger than the no risk pyramid. So if we go back up here a minute, let's go back up and look at these graphs. It's a little more obvious here. We can see that the amount of inherent variation, we measure that by the margin of error if you recall, the margin of error here for this group is going to be larger than it is for the no-risk group. Okay, so that pyramid for the no-risk group is actually pretty skinny, which makes it easier for 20 to be an outlier. So even though my squared distance isn't as large, it's actually more of an outlier in the no-risk group compared to the great risk group. Now, we don't really have to worry about that too much for the slight risk and moderate risk because they are really close to the middle. So what is the problem here? Well, the problem is that our current measure of extremeness, which up to this point we've been using just distance squared, does not take the starting or ending location into consideration. So the fact that this pyramid is not very far up the number line, that its expected count is down here at 10, okay, being 10 off when I'm talking about values around 10, that is quite a bit. Okay, but being 10 off when I'm talking about values around 50, that isn't so much. So our measure has to take this into consideration. So what we're going to do instead is just compute an adjusted distance squared quantity. And we're just going to simply divide that by the expected number here. So we're going to take the distance that we were looking at before. So the numerator here is just that observed minus, the numerator is the observed minus the expected, that thing squared. I'm just going to divide that distance by the expected. I'm going to do that for every single category. Okay, so I'm going to take this distance here, which is 10, going to square it, so I'm going to end up with 100, and then I'm going to divide it by the expected quantity. So I would divide that by 10. And I would do that same calculation for each group. Once I have that calculation done for each group, then I just simply add them up across all of the categories. And when I do that, we call that result a test statistic. Okay, so that adjusted squared distance added up or summed up, this just says sum it up across all the categories, we call that quantity a test statistic. Now, just a quick comment here. The issue of needing to have a reference in understanding a measurement is not unique to this situation here. Let us, for example, suppose that I said someone got a $2 an hour raise, and I ask you whether or not that's a lot. So is a $2 an hour a raise a lot? Well, it depends. If the person is working a low-paying job, let's suppose they're getting $8 an hour, then a $2 raise is a lot. However, if the person is a lawyer who's making $275 an hour, then a $2 raise is inconsequential. So what you would do in this situation is just look at the $2 raise relative to where you were starting from. You could kind of almost compute like a percentage. What was the percent raise would be a way to alleviate this problem. You can kind of think of this as a percentage. I mean, it's not technically a percentage because the expected is not a total here, but we're trying to put that square distance relative to where I'm starting from. So relative to the expected quantity here. Now, what we have been describing is what's called a Pearson chi-square test. And if the wiki entry for that is shown here, let me blow that up maybe a little bit for you. And you can see that the test statistic, it's called the Pearson's test statistic. Okay, they've used this script chi-square to denote that. Is simply you take the O, which is the observed numbers, subtract the E's, which are the expected numbers. They have an index I here just to indicate the different categories. But they're taking the observed minus the expected. They're going to square that there. Again, we're doing that squaring so we can avoid that canceling out effect. And then I'm going to divide that by the expected. Again, dividing by the expected makes that squared distance relative to something. Now, I suppose we could look at a chi-absolute test as well. So instead of doing squaring in here, we could put absolute values in there. Now, we don't actually do that. As I've stated previously, we use the squared version of these distances. Okay, so now let's go ahead and compute that test statistic quantity for the data that we obtained from our study. So we're going to take that distance squared and simply divide each of those by their respective expected quantities. So here for the no risk group, we're going to take the 20 minus the 10. We're going to square that. We're going to get that 100 like we had before, but now we're going to take that 100 and divide it by the expected number for that category. So 100 divided by 10, I get a value of 10 there. So for the second category, for the slight risk group here, let's go ahead and just zoom out a little bit. For the slight risk group, I'm going to take 31 minus 27.5. I'm going to square that quantity. I get 12.25. And then I divide that quantity by 27.5. Again, the expected for that particular category. And when I do that, I get a very small value of 0.45. Going to do that for the moderate risk. I'm going to take the 6.25 value and divide it by 37.5. I end up with something very small here, 0.167. And then finally, for the great risk category, I'm going to take that minus 11 squared, which is 121, and I'm going to divide that by 50, because that's the expected number there. And when I do that, that ratio becomes quite small here at 2.42. And then I'm simply going to add those up across all four of those categories. So I'm going to take 10 plus 0.45 plus 0.167 plus 2.42, and I get a value here of about 13. Now I do want to just bring to your attention that the biggest distance from the expected now is this first category. Okay, so the no risk group. So after doing that adjustment by dividing by the expected, you can see now that that is certainly the biggest adjusted distance from the expected. Over here, that great risk group, that quantity is brought down to 2.42, which is still somewhat larger than the other two, but I would say that's a moderate distance away from the expected. How do we obtain the reference distribution? Actually, let's go ahead and take a pause again. These videos get kind of long and drawn out. And I did think of something that I want to share with you, that these aren't the only videos that I have on YouTube. There's actually a video of me riding in a little red car that I'd like to show you. So this is me here, a couple of years back, riding in a little red car that is meant for kids, but I thought I'd give it a try. So I hope you enjoy the video.
Big man in little car. I'm recording this. I'm recording it.
Well, I hope you enjoyed that video of me riding in a little red car. If you YouTube, or if you search big man and little car, you should be able to find that video. All right, let's get back to finishing up these notes. We need to obtain the appropriate reference distribution for this quantity 13.03. So I would do that in the same process that we did before. I just need to use the same exact calculations that I use on my data on those outcomes that I obtained from pulling out of the hat. Okay, so the outcomes that I obtained here from that hat, we talked about those when we constructed those reference distributions. The 13, 24, 32, 56, the 8, 27, 37, 53 patterns. I just need to do that test statistic calculation on each one of those simulated outcomes. I can use a spreadsheet to do that, and that's what's shown here on the bottom of page, wherever we're at here, 23. I'm going to compute the sum of those, or the total of those. That's what I have over here on the right-hand side. Okay, and then I'm just going to plot those values, and that's what I have here. So this reference distribution on the bottom of page 23 is my reference distribution from my simulation model. I'm simply going to identify the proportion of observations that are greater than 13.03. And it looks like I have one. In this particular graph, I obtained 250 simulated outcomes. So 1 divided by 250 is 0.004. And that's going to be my p-value here. Again, if I'm far up on the right-hand side, I'm going to say that I'm far from the expected quantities. When I'm back here close to 0, then I'm close to the expected quantities. So let's go ahead and finish up here then. The research question was, is there enough evidence to suggest that grade 11 students, grade 11 students from Fillmore County deviate from the historical patterns of other students throughout the state of Minnesota? The p-value for this test is 0.004. Again, I'm just determining the proportion of dots that are greater than 13.03. Is 0.004 less than 0.05? It is indeed less than that. So therefore, I do have enough evidence for the research question here. Writing a conclusion then, we do have enough evidence to say that grade 11 students from Fillmore County deviate from the historical patterns of other grade 11 students throughout the state of Minnesota. That statement is made with a p-value quantity of 0.004. Now, a quick couple of comments before leaving section 3.2 here. The research question posed above asked whether or not the proportions for Fillmore County deviated from the trends from the rest of the state. Okay, the test conducted here was a two-sided test. Now there is a one-sided test that might be more informative. In particular, a research question such as, do the grade 11 students from Fillmore County have more lax perceptions regarding substance abuse of alcohol? Well, that would be a one-sided test. Unfortunately, we cannot do a one-sided test of this nature. And in fact, one doesn't even exist. Maybe one of you will decide to be a statistics major and figure it out for us. If not, we're just going to have to live with the two-sided tests that we've described up above. When comparing the observed counts to the expected, it appears that the perceptions of grade 11 students from Fillmore County are indeed more laxed. So if we go ahead and just look at what we have for the observed outcomes, which are the bars, and then the expected outcomes for no risk was 10, 27.5, 37.5, and 50. You can see on the lower end of this distribution that the observed counts are actually higher than expected. And the lower end of this distribution is the more laxed opinions about alcohol abuse. On the high end, the numbers from Fillmore County are actually somewhat below the expected counts. So great risk and moderate risk, we don't have as many students saying that alcohol is of great risk in this particular situation. Also, the name of the test that we just talked about here is a chi-square test. The chi-square test is one of the most common tests used, and it's one reason we spent a lot of time talking about its development here. Now, to complete this test, you can use software packages. And in fact, you can use online apps to get this done as well. In Google Sheets, we would just use the equal chi-test function. and it'll go ahead and compute the p-value for us directly. All I need to do, and we'll talk more about this in the next section, is just type equal chi-test. I need to put in the range of cells that contain the observed counts, which would be the 20, 31, 35, and 39. In my particular sheet, that range of cells goes from C3 here over to F3. So that's what I've entered in here. And then I have to have a comma. I need to separate the observed counts from the expected counts. The expected counts in this particular spreadsheet sit in cells C4 through F4, so I would just enter those in there. Put the parentheses at the end, and what is returned here is the p-value quantity. So Google Sheets and Excel will use the chi-test function in order to get this done, and it returns a p-value for you. Now these software packages and the online apps use the theory-based approach of the chi-square test, and the chi-square distribution in particular. Just like the binomial probability distribution, the theory-based approach here is based on an infinite number of repeated samples. So that's kind of the best case scenario. And we can see that the theory-based approach, or the chi-square distribution that's shown here, mimics quite closely the simulation-based approach that we used up above to compute the p-value. Okay, that does it for section 3.2. We will show you several examples in section 3.3 of using a spreadsheet to compute the chi-square test. Okay, thank you.